Getting a bigger picture of forecast accuracy. Graphing variances and performing statistical calculations on variances are two ways to get a bigger picture of forecast accuracy. Some people are optimists, and some people are pessimists. Some people see the glass half full, some see the glass half empty. Some people are constantly predicting huge numbers that are never achieved. Some predict low numbers that are constantly exceeded. We're all human and subject to biases. Throw in performance evaluations and bonus plans, and we're all trying to manage expectations to exceed them. When we want resources, we make big promises to justify the costs. Forecast accuracy suffers from all of this. One way to detect patterns of bias is by graphing multiple forecasts against the actual results. The x axis of this scatter plot graph is the forecasted amount. The y axis is the actual amount. If we were clairvoyant, our forecast amounts would equal the actual amounts and would fall on the upward sloping line. I won't speak for you and your company, but my coworkers and I have not been so accurate or lucky. The best we can hope for is a graph where dots lie slightly above and below the line, like this one. I'll discuss common sources of forecast error in a later lesson. One of them is overoptimism. In over-optimistic forecasts, the forecasted amounts are always more than the actual amounts. This graph shows dots consistently falling to the right of the line where forecast equals actual amounts. Sandbagging is a term for forecasting amounts that are consistently exceeded. Here is a dot plot for a chronic sandbagger. These graphs are diagnostic tools. They identify a problem but don't tell you how to fix it. Admitting you have a problem is the first and very big step to recovery. As I worked with people, I began to learn who gave me high numbers and who gave me low numbers. With budgets, I had to put in the budget whatever was approved by their supervisor. I could push back against those numbers. The graphs we just looked at are a way to show bias. At the end of the day, it was their numbers or a compromise set by a senior leader or committee. Forecasts were often my numbers. I could adjust the source information to amounts that I believed to be more accurate based on past variances. In essence, I was shifting the dots to the line to remove potential bias. The amount that dots need to be shifted can be determined by some variance statistics that we'll now look at. Some simple calculations can show us how much our forecasts have been off in total and as a monthly average. Here is the data set I used for the neutral bias graph that we looked at earlier. The monthly forecast error is simply the actual amount minus the forecast amount. In other words, row 4 minus row 5. The total forecast error in cell N6 is only $3. Note that I have rounded almost all dollar amounts to the nearest dollar. The average error in cell O6 is only $0.25. As always, I have also used small dollar amounts for ease of presentation and explanation. Feel free to add as many zeros to the end of the numbers to make them feel real for your company. The $3 cumulative error is only 0.18% of the total forecast amount of $1,593. I would be ecstatic to have such a low forecast error over a year. I'll show later how I could have the same low total forecast error, but horrible monthly variances throughout the year. Row 7 calculates the mean absolute error. Each month, I calculated the absolute value of the forecast error. The formula for cell B7 is the absolute value of B6. The sum of all these monthly absolute amounts is $45, which is in cell N7. To get the mean monthly amount, you divide the $45 by 12, in other words, 12 months, to arrive at a mean absolute error of $3.75. For you math formula fans, my description of the calculation can be summarized as the mean absolute error equals 1 divided by n times the sum of the absolute values of actual minus forecast. The total cumulative error was only $3, but a mean absolute error of $3.75 means each monthly variance is likely to be larger than my $3 total variance. Summing the absolute values of the variance exposes offsetting variances that the total cumulative error obscures. To get a context of our absolute errors in relation to the actual amounts, we can calculate the mean absolute percentage error, or MAPE, which is in row 8. For each month, the absolute value of the forecast error is divided by the actual amount. The sum of those percentages, cell N8, is divided by 12 to arrive at a MAPE of 2.9% in cell O8. Now, I will show you why we often can't just use a simple sum or average of the forecast error. This table is the same as the last slide, but the monthly errors are $50 higher for positive errors and $50 more negative for negative errors than the original table. The total and average forecast errors are still $3 and $0.25 in the updated table, which I've circled in red. However, the mean absolute error is now $53.75, and the mean absolute percentage error is 52.4%. I circled these numbers in blue. The absolute value function of the mean absolute error and mean absolute percentage error is absolutely valuable for capturing the volatility of forecast errors. And yes, that was a terrible math joke. I had a boss once who said there will always be errors in budgets and forecasts. You just hope for offsetting errors. Offsetting monthly errors can hide in the sum of forecast errors. Offsetting volume and rate errors can result in a total error of zero. Mean absolute error and mean absolute percentage error exposes offsetting errors that occur over time. Breaking out the volume and rate variance components can expose offsetting errors. I'm showing mean absolute percentage error because it's a common forecast statistic. Many people don't like it because it can throw out some very large amounts when there are low dollar amounts. It will result in an error if any month's actual amount is zero. It puts a heavier penalty on negative errors than positive errors. A similar statistic is WAPE, which stands for the weighted average percentage error. The WAPE is easy to calculate. It's the sum of the absolute value of the monthly actual amounts minus the forecast amounts divided by the absolute value of the sum of the actual amounts. I also show the formula here for you formula fans. The WAPE of our example starts with the sum of absolute values of the forecast errors in cell N7, which is $45. That's divided by the sum of the absolute values of the actual amounts. Since my actual values are positive numbers, we can just use the sum of actual values in cell N4, which is $1,596. The WAPE is then $45 divided by the $1,596, which equals 2.8%. Here is an example that shows the difference between MAPE and WAPE. This example is a seasonal company whose sales are high in the summer and low in the winter. Their MAPE is 7.9%, but their WAPE is only 4.1%. In other words, $94 sum of absolute errors divided by the $2,302 total absolute actual. In MAPE, all variances are weighted equally. In WAPE, the total percentage error is weighted by the actual amounts. If the thought of using statistics to measure forecast accuracy makes you giddy, I'm happy to say there are more formulas to use than you can shake a square root at. Here is a quick summary of some options. The weighted mean absolute percentage error allows you to weight each month, which is useful if some periods are more important than others. Another option is to use the actual amounts as the weighting. The symmetric mean absolute percentage error is a variant of MAPE that addresses MAPE's issues with zero values. The mean squared error is the average of squared differences. It penalizes large errors more than the mean absolute error. However, it's a squared number in different units, making it hard to explain. The root mean squared error is the square root of the mean squared error. This provides a squared metric in the original units. It's more sensitive to large errors than the mean absolute error and can be overly influenced by outliers. The mean absolute scaled error compares forecast error to a naive baseline, making it scale independent. To be honest, I have no idea what that means, but I included it in this course if it sounds interesting to you. This formula handles values near or equal to zero better than MAPE. Unlike the earlier measures, it penalizes positive and negative forecast errors equally and penalizes errors in large forecasts and small forecasts equally. Mean bias deviation shows whether forecasts are over or under the actual amounts. It's a quick formula to show bias, but the graphs I showed earlier may be more intuitive, informative, and compelling. Any metric must be understood for it to be informative. The cumulative forecast error, mean absolute error, and WAPE I began with are fairly easy to understand with a little explanation. The other formulas may be more accurate and informative in certain situations, but will require more explanation for general audiences. They may be better for analysts to monitor. If one of those formulas identifies an issue, the underlying cause and its implications can be presented without reference to a formula. We can now calculate the amount to adjust forecasts. Once we have a set of forecast and actual forecast numbers from someone, We can use the calculations we just saw to estimate their forecast errors and biases. We might then be able to adjust future forecasts from them using those calculations. This is a graph of an overoptimist. I've calculated the WAPE for their forecasts. However, I've weighted the WAPE by the forecast amounts, not the actuals. In other words, the WAPE is the sum of the monthly absolute variances divided by the total of the forecast amounts. I'm given forecast amounts, not actual amounts, so I want to calculate a number to adjust the forecast amounts. The WAPE is 11%. I can then adjust the forecasted amounts by the WAPE. Each forecast amount was multiplied by 1 minus the WAPE. For example, the calculation for January is $100 times 1 minus 0.11, which equals $89. The forecasts are now much closer to the actual amounts. Remember, forecasts equal the actual amounts along the upward sloping line. That worked fairly well because the slope of the forecast values to actual values was close to 1, which is the slope of the line where the forecast amounts equal the actual amounts. I ran a trend line through the forecast in this image and showed the equation for the line. The slope is 0.97, which is very close to 1. What if the forecast to actual line has a slope different than 1? How can I adjust the forecast? Here is a new set of forecast amounts compared to the actual amounts. I've once again ran a trend line through the forecasts and shown the formula for the trend line. The slope is 1.27. The intercept is minus 41.74. These two numbers will be important later. Can I just adjust this forecast by the WAPE weighted on forecast amounts? I've calculated the WAPE to be 5%. Here are the forecast amounts adjusted by the WAPE. The dots are now closer to the upward sloping line, but their slope is still wrong. In this graph, I've adjusted each forecast amount by the line trendline formula. The updated forecast amount is original forecast times slope minus intercept. January's updated forecast is calculated as $100 times 1.27 minus 41.74, which equals $85. Both the slope of the forecasts and their distance to the upward sloping line have been improved. These are two ways to adjust bias in forecasts you receive or that you detect in your own forecasts. If you have seasonal actual amounts, you could use the monthly variance amounts in the past to adjust the same months in future projections. The general rule is to identify the shape of the initial forecast, the shape you want it to be to match likely actual amounts, and adjust the forecast to the desired shape. You might use a simple mean percentage adjustment like I did with WAPE to shift by one dimension. You may need to use a line equation to shift across two dimensions. There have been times when I've taken another approach to forecast data from others that I found to be unreliable. I worked at a bank where the lending groups would provide future loan growth that often differed from actual growth. I began to show loan projection graphs with both their balances and a simple trend line based on past actual growth. My job was to manage our bank's liquidity, so we were ready to fund either growth line.